Dear colleagues, so let's start today's seminar. Today our speaker is Valentin Iliev, and he will talk about on pairs of non-commuting Hermitian operators on the unitary plane, which are permutable measurements. You may start.
Okay, I have permission to begin. First, I'd like uh, to clarify the meaning of some words in the title because I see that not many people are not physicists, so it's necessary to do that. So I'll begin with the context, and the context of this presentation is quantum mechanics, or as it is modern now, quantum theory. And I begin with several axioms of quantum mechanics. This axiom one is the principle of superposition. Any physical system, electron, hydrogen atom, and so on, can be associated with the unitary space H with inner product denoted in this way. This is the Dirac notation. And we assume that it is linear in the second slot and anti-linear in the first slot. So the corresponding norm make it a Hilbert space. So the non-zero vectors in this space are called psi functions, and the normed psi functions, norm means the norm is one, are also called wave functions. Chronologically, the physicists started with psi functions, and the statement that psi1, if psi1 and psi2 are psi functions, then any complex linear combination is a psi function, is included in this axiom. But this is, in fact, it is just the C linearity of our space H. So it is included automatically. The second axiom, second postulate, is the postulate about observables. Any physical quantity of the system, position, velocity, energy, and so on, is represented by a Hermitian or linear operator which is defined on the space of states or space of chief functions. It is said to be observable. Its spectre, we know that the Hermitian operators have real spectre, so its spectre coincides, this again included in the axiom, coincide with the set of all values of this physical quantity obtained after measurement. They are the eigenvalues, in fact. The corresponding eigenvectors are usually normalized psi functions, states of the physical system. If we denote by ui, then if the physical system assumes the physical system is in state ui, then the physical quantity assumes the corresponding eigenvalue lambda I with probability 1. And we fix an orthonormal coordinate system of H. Of course, I'll consider the finite dimensional space, finite dimensional case. The most important case in quantum theory, quantum mechanics, is the infinite dimensional space, but we'll not discuss it here. Even we'll discuss the two-dimensional case here. So any state can be represented as a linear combination with those coefficients, obviously, because this is an inner product, and the square of the absolute value of those coefficients, which are complex numbers, is just the probability that after the measurement, the quantity will obtain a value lambda ui. We define the sample space, this sample space, it is obvious. We take the eigenvectors, u1, u2 up to un, and to any eigenvector we assign this probability. And because we assume that psi is 1, norm with norm 1, then the sum of all those coefficients is 1. And then some formal considerations. The image of this sequence, there are probably repetition there of eigenvalues of A is the spectre of A. And for any lambda in the spectre, we do not but U lambda, the inverse image. Then the probability of this U lambda is just the sum of all those, uh, all those I which are in all those coefficients which are in with indices in UI. We consider this operator also as a random variable on the sample space, this sample space, with this probability distribution. Here it is written, this probability distribution. So in other words, we identify the event U lambda in this sample space with this event A equals lambda, with this relation, in fact, A equals lambda. And just because this identification, we can call this relation A equals lambda also an event. And then we can, then of course, the probability of this A equals lambda is just the probability of that event in the sample space U lambda. And now, what happens when two such operators commute? AB is equal to BA. Then there exists, we know very well that there exists a orthonormal basis consisting of eigenvectors of both A and B. Then the image of the sequence of eigenvalues of B is the spectre of V, and by analogy, we define this V mu. This is the inverse image of any mu in the spectre. And by S psi AB, the corresponding sample space. So the event B equals mu, this relation, is can be called event because we identify with V mu. And then you have, in the same way, the probability of this B equals mu is probability of V mu. And now what is important, this event, the intersection U lambda and V mu exists. Of course, this is the intersection of two events in a classical sample space. And we identify this event with the conjunction A equals lambda and B equals mu. And this identification allows this conjunction to exist, of course. So this is in case of two operators that commute. And we call two measurements simultaneous if the corresponding self-adjunct operators, this means Hermitian operators, commute. In particular, the probability of getting as a result of two successful measurements, this pair lambda I mu j doesn't depend on the order of the measurements. And in contrary, if A and B do not commute, then in general, the probability of obtaining this ordered pair, lambda I mu j, is different from the probability of getting the ordered pair mu j lambda I. So the corresponding obvious notations are this. Here, this probability, first A, then B, is not equal to the probability of B then A. So this is in general, but it turns out that there are exceptions. And there exist non-commuting pairs A and B of Hermitian operators, which are permutable. Permutable by definition means that these probabilities are equal. So the result doesn't depend on the order of taking those measurements. And we have a theorem here in this presentation that it characterization of those non-commuting pairs A, B of Hermitian operators on the unitary plane. So we consider very particular case when the unitary space is unitary plane, and we find some pairs A, B of non-commuting operators which represent permutable measurements. So we consider non-commuting Hermitian operators A, B with this spectre 1 minus 1, written as 2 by 2 matrices in terms of polar coordinates. Here are those matrices. In general, this is the general representation of those matrices that corresponds to Hermitian operators with spectre 1 minus 1. And we consider another copy of this operator A, which we denote by B, but it is different from A because nu and zeta are different from mu and theta in general. And the corresponding eigenvalues are lambda 0, 1, and lambda 1 is minus 1. This is just a notation. And here is the corresponding orthonormal eigenvectors. See, this is a strange notation because there are neither cosine nor sine, but they are included here. And I'll explain how we can define this TRK of some angle. Let's go back to the notations. We consider the field of two elements, Z2. It consists of two elements, 0 and 1. And moreover, we define an external law of composition, 0 times x equals 0 and 1 times x is x, on the set of all real numbers with this field, Z2 as operating set. This law satisfies those properties, very, very natural properties, but I would like to underline that R, the set of all real numbers, is not a Z2 module. Just because an important property is not satisfied, namely k plus s times x is not equal to k times x plus s times x. So this is not a Z2 module. R is not a Z2 vector space, in fact. And but those properties are satisfied. We, as usual, we denote this factor ring in this way. I identify its members with the interval 0 to p. It's written here. H is the two-dimensional unitary space with this inner product in Dirac notation. We discussed this. We fix a basis which is called computational basis. Those 0 and 1, orthonormal frame for H. So those 0 and 1 they do not coincide with the members of Z2, of course. U script the unit sphere in H, E, the three-dimensional R-linear space consisting of Hermitian operators on H with trace 0. And it is well known that all of them are invertible linear operators except the 0 operator. And by SE, we denote the unit sphere, and the spectre means the spectre of the corresponding operator, and we fix an orthonormal frame of H formed by eigenvectors of this. And H, AI are the eigenspaces, and these PI A are the corresponding projections defined in a natural way. And now we define this sample space. We discussed it, but sample space in this particular case when the orthonormal frame consists of two vectors. With this probability assignment, we discussed this in general, so I'll omit this. And finally, for any member of Z2, 0 and 1, and for any alpha any real number, we denote in this way the cosine of alpha. TR0 alpha is cosine of alpha. Sorry, TR1 is sine of alpha. So that's why after introducing this notation, we can write down the corresponding orthonormal eigenvectors of A, of this A, in this form, this very symmetric form. And this is a kind of internal Z2 symmetry in the set of all trigonometric identities in the planar trigonometry. So we continue to assume that A and B are not commuting operators, but this is equivalent to B is not plus or minus A. In this case, they do not commute. And this property, this relation reads in this way. Either B is equal to A, this mu equals mu and theta equals zeta, or B is equal to minus A, which means those two. So we do not consider those cases. And one of the three equivalent conditions in our theorem is that the polar coordinates of A and B are solutions of this, some member of the family of equations of this form. Here, epsilons, here these are the eigenvectors of A and B, and these are complex numbers. Epsilons are complex numbers with module 1 over square root of 2. Moreover, the common value of the above linear combination of eigenvectors is an initial state C, such that the corresponding A and B do not commute and are permutable. So we here, in order to give examples, here we consider very particular case. Those four complex numbers are just plus minus 1 over square root of 2. And then the simplified version of this equation is this equation, and we will solve this equation for any four-dimensional vectors in this Z2 linear space. And they'll give you examples of non-commuting Hermitian operators, which are permutable measurements. And this is a fundamental lemma that allows us to calculate some expressions in general. So here, this identity, this is generalized identity. Trigonometric identity depends on two parameters, k equals 0 and 1, and t equals 0 and 1. So there are four trigonometric identities of that kind here. And we can write down this in a uniform way. And we omit the proof, but we used the following generalized trigonometric identities here. They are written here. So once again, any of those generalized trigonometric identity encodes some set of usual trigonometric identities. And now we'll consider a sequence of any two consecutive members are non-commuting operators, and moreover, they are in the unit sphere of they have their matrices have the form we discussed just several minutes ago, and let psi be the initial state of the quantum system with PIA of C different from zero. This means for I equals Z2. This means that Psi is not an eigenvector of A. After the measurement via the observable A, in accord with the reduction of wave packet, the state of quantum system changes in this way. Psi is this vector. This is for some I in Z2, which is a unit vector in the one-dimensional eigenspace HAI. But there is another unit vector there. This is UAI, and we can suppose that they are equal. Psi is this unit vector UAI. Further, if you apply the projection of B on this J projection of B on this vector, it is not zero for all J's in Z2 because otherwise the both operator will commute. Will commute because this eigenvector of A belongs to eigenspace of B, and also this happens, which is a contradiction because A and B do not commute. So after the measurement of observable B, the state of a quantum system changes to Psi Ij, this vector, but this is a unit vector in the one-dimensional space HJB. So we can suppose that it is UJB. So we continue in this way and we obtain the following sequence of sample spaces here. And now we'll consider those sequences for two operators, A and B, in this order, A, B. We get those equalities, the probability of A equals lambda I in the sample space that corresponds to Psi and A. This is this absolute value according to the Born rule. And the probability of B equals lambda J in the sample space, this sample space here, it is equal to this square of the inner product of those two vectors. And then thinking of the probabilities in the above equalities as relative frequencies, we use Born rule, the definition of conditional probability, and obtain this. See, this is the probability of A equals lambda I. We discussed this, and this conditional probability, under the condition that A equals lambda I, the probability of B equals lambda J is this absolute value. So using the corresponding multiplication rule and the obvious notation, we can write down this formula for the probability of A equals lambda I, and then, so first the measurement I is taken and it gives result lambda I, then the measurement B is taken and it gives result lambda J. And this is the corresponding expression. And we can consider also the sequence BA, and we have this identity here, this identity. And here is the technical lemma that says that those absolute values, which are written here, are either one value p when I is different from j, or 1 minus p when I is equal to j. And here is the main theorem of that work. We take non-commuting invertible operators A and B, and let Psi is a unit vector, and which is neither an eigenvector of A nor an eigenvector of B. Then the following three conditions are equivalent. For all ij in Z2, in the field Z2, we have this equality. This means that the measurements A and B are permutable by definition. The second equivalent condition is that all probabilities of the events A equals lambda I and events B equals lambda J are 50%, one half. And the third condition, equivalent condition, is that psi, the initial state, has this uh, expression with those complex numbers that have value one half. And we discussed this. So this repetition, we say that under the condition of the third statement on theorem 3, we call the corresponding measurements A and B permutable of signature, this sequence of numbers. So here is the general form of operators with spectre 1 minus 1, invertible, of course, invertible. Corresponding eigenvectors are those, and we discussed this. I'll not. Now through the end of this presentation, we consider the particular cases, those particular cases, and then we get that square root of 2 of times c is this expression. So our idea is to solve those equations here for any four-dimensional vector a0, a1, b0, b1, and we found the solution of this equation in terms of polar coordinates. In this way, we produce the initial state C of the quantum system, for which the measurements of the non-commuting observable of A and B are permutable. And well, this we discussed this lemma. And now we write this equation in this form. And using the above lemma, we have this, it's equivalent to the following two equations. This system of two equations. And we consider two cases when B0 plus B1 is A0 plus A1, and B0 plus B1 is 1 plus A0 plus A1. Remember that those are members of Z2. And now here I begin with calculations, long calculations and tedious calculations, but as a result, I'll omit those calculations. I think it's not very interesting. If you want, you can see my paper in ResearchGate, my preprinted ResearchGate, when those calculations are made. All of them are made. It turns out that all calculations give you adequate results, I mean natural results, which shows that we are on the right way. And finally, I omit those calculations. Finally, we get nine pairs of operators A and B, and the corresponding initial states of the quantum system. Under these conditions below, the pairs A and B are non-commuting and permutable. And here is the list of those operators A and B in terms of polar coordinates and the corresponding initial state of the quantum system. Here we have 9 such pairs A, B obtained via solving those equations. So we find complete solution of this for this particular case when all epsilons are plus minus 1 over square root of 2. So this is in fact more or less the content of that presentation. If you have questions, please ask.
Thank you very much for the nice talk. Are there questions or comments?
Hello, can you hear me?
Yes, we can.
Uh, so it's really interesting because in the textbook we learned that you need to be commutative in order to have permutable probabilities. And I have a guess that this has to do with so-called CPT symmetry. CPT stays for charge, parity, and time. So have you ever looked in this direction?
No, thank you for
So
your.
these are some discrete Lorentz symmetry. You have the Lie group, but the Lie group has several layers, branches, and according to for the standard Minkowski space, you have like four connected components, and they are interpolated by Cp and T. Well, this is ordinary quantum mechanics, so you should not care about Minkowski space, but nevertheless, there is some, it's a non-relativistic theory, but I think that there is something because 9 is 8 plus 1 and 8 is 2 to the power 3, like you have 3 independent or almost independent, because they are not completely independent, discrete Z2 factors, and then some and one at the top. So I would search connection with the discrete symmetries of space, time, and charge.
So unfortunately,
Yeah.
I
Okay,
haven't considered this in this direction.
but this is people usually forget about these symmetries, but they are important.
Yeah, I'm sure. I'm sure they're important, but I
And
didn't.
this is just a guess, and this is just a guess.
Thank
I
you,
cannot.
Todor.
Yeah.
Thank you.
More questions? If not, let's thank our speaker.
I have a very superficial amateurish question.
Okay.
The title gives the impression that there is a contradiction with the commonly known thing that the commuting means possibility for simultaneous
Permuting
measurement.
measurements
So
and commuting.
Here, at least on the face of it, it looks as if this is not an equivalence. So there can be a simultaneous measurement without commuting. So where is the catch? How it is explained that there is no contradiction between what is in the talk and the established statement?
I gave a definition of permutable measurements. This means those two probabilities commute here. So it doesn't matter if you apply first measurement A, then measurement B, and measurement B, then measurement A. You get one and the same pair of results. This is
Here
this is a probability definition of of permutable measurements, and commuting measurements is another story. The operators commute. Yes.
So these are conditional probabilities here with the
Yes.
semicolon, not a slash.
Yeah.
Okay.
Yes. Moreover, I suspect that one can, based on this equality, one can build a Boolean algebra with those events, those relational events, and their intersection under this, which is defined under these equalities. But this is, I haven't considered this. This is just an idea. Probably some generalized Boolean algebra can be defined. So this is my answer, in fact.
Thanks. Thank you.
And Valio, may I ask you?
Yeah, yes, Todor.
So you probably considered also more states like triquets, or how was their called? These are qubits, no? Here.
No.
Your
This is my consideration for two-dimensional H.
Yeah.
I mean, the operators have
because
this
for
form.
three-dimensional there will be, I guess, well, it will be a little bit longer, but you should have some something similar.
I don't know.
Something similar. Yeah. Well, and this is this will be the next example, which can give the general statement. Let's say if it's CPT or if it's something else. This will be the.
You mean for three operators?
Well, you have three states which are interpolated by some special matrix, which is so here basically you have quaternions, right, acting on these two states. I would say.
Well,
I would
haven't
call this
considered
algebra
this. Sorry.
quaternionic. So, well, there is a natural thing in three dimensions, which usually goes under the name qubits or something like qubit and qubit, binary and triple system. So, and this should not be very difficult to look once.
Thank you, Todor, for this idea. Thank you.
Other questions? If not, then let's thank the speaker for the nice talk and let me stop the recording.